In today's video, we're going to build on our understanding of the position and momentum space wave functions and come to one of the more sort of famous things in quantum mechanics, at least in pop culture, the Heisenberg uncertainty relation. Start this off, I want you to imagine holding a string and shaking it so that you send a wave along the string. So the wave on the string would look something like this. Now, if I were to ask you what is the wavelength of that wave, you would be able to give me a pretty exact answer. You just look at how long one of those wavelengths exists, how long it is, measure it, and say, all right, that's my wavelength. But if I were to ask where is the wave, you would give me a much less precise answer. That wave kind of exists everywhere on the string, and it's going along, so you wouldn't be able to answer that quite as accurately. Now, if you take that same string and if you were to imagine flicking it just once and sending a pulse down the string, if I were to ask the same sort of questions, what is the wavelength of the wave? Then this time you would have a hard time answering that. You wouldn't be quite so sure. It doesn't even have a full wavelength or anything for you to measure. Whereas if I asked where is the wave, you could probably give a pretty accurate answer to that because it's just that one, well-defined pulse. It has a good location uh, uh, associated with it. And so we see there's this sort of trade-off between, wavelength and position of the wave, and we've been seeing the same sort of thing in our wave functions in position and momentum space. Right there, if you think about momentum, the eigenvalue for that was h bar k, and k is the wave vector, so related to wavelength. So if you know the momentum very well, you're essentially saying you know the wavelength, um, but at the same time, you don't know as much about the position and that. And that's sort of the heart of what the uncertainty relationship that many of you have probably seen before is. If you recall the issues we had when we first discussed what our momentum eigenstates were, right? So they had this sort of they had this form, and if you were to choose, I'm in this momentum eigenstate with a well-defined momentum eigenvalue p, your wave functions would look like this. In momentum space, you have that well-defined P naught, and the entire and in momentum space, that the entire particle has that momentum. It's got that one well-defined value of momentum. So that's what your momentum space wave function looks like. But if we look at the position space wave function of that eigenfunction, we have just a wave that sort of spans everywhere. This is the real part. The imaginary part would look similar. And this gave us sort of an issue with normalization and some of the problems we had, where if you take the amplitude squared, or the magnitude of that wave function in position space squared, you see that it has a finite value everywhere, and you can't really define a position for that particle. It's localized. So you have this extreme case where you have an exactly defined momentum and a not at all defined position for that particle. Turns out the reverse is true as well. So if we think of a position that is precisely defined, we have a particle who is defined at an exact position. So the wave function is the Dirac delta function at that given position x naught. Its wave function in position space looks like this. Now, its momentum space wave function is just going to be the inverse Fourier transform of that. So we take this sort of momentum eigenstate and integrate the position wave function over all space there, and we get that momentum space wave function for a particle in the position eigenstate x naught, and it looks like this. We have a wave spanning through momentum space that again doesn't have, if we were to take the real part and then take the amplitude or magnitude of that momentum space wave function squared, it would span all momentum, and we would have like a poorly defined momentum for that particle. So again, what we saw was this trade-off between how well we can know momentum and position at the same time. Just keep chugging through the examples we've looked at. If you think about our discrete superposition example we went through in the other video, we had chosen, three momentum eigenstates, one at a central momentum of p naught, and then two shifted by delta p naught to the left and the right with half the amplitude. So these are spread about plus or minus delta p naught. We could sort of ascribe an uncertainty to how well we know that momentum for this particle by saying plus or minus delta p naught. And our wave function, our position space wave function, looked like this. What happened is, if we take the superposition of these momentum eigenfunctions, we had, these three wave functions that added together, and it caused this sort of destructive and constructive interference pattern that localized that particle into a wave packet, right? So in position, we had a wave function that had a, roughly here, we knew the position to plus or minus some delta x, where the size of that wave packet. And how that worked was, well, the wave packets, these destructive interference points, these nodes, essentially occurred when the phase difference between the elements that were making up our wave packet were at a phase by pi, right? So, these wave functions are at troughs, these are at crests, so they're at a phase by pi. The phases are, these exponents. So what that meant was, the difference between the phase in those two exponents is equal to pi at those points when it's at when we're at whatever this delta x is. So we can use that and solve for that delta x. This term is going to cancel with this term, and we're just left with the delta p times delta x over h bar is equal to pi. And we have a sort of uncertainty relation of the uncertainty in momentum times the uncertainty in our position is equal to some, h bar pi. Now this is essentially the Heisenberg uncertainty relation. It's not the exact one that you're familiar with and not the true one. And that's a result of us, again, we're only using a discrete superposition and we need to use continuous superpositions to properly describe these. But it really sort of gets at the relationship between momentum and position. And we can't know both of these things because of this sort of the wave-like nature of the wave functions in position and momentum momentum space. So what it really comes down to is these position and momentum are incompatible observables. If you recall, we had uncertainty relations when we were talking about our spin 1/2 systems. The ones we looked at were the uncertainties in the spin operators. So delta Sx, delta Sy, has an uncertainty relation that's greater than 1/2 the time average, the magnitude of the time averaged commutator of those two operators, right? So in the spin 1/2 case, the commutator between Sx and Xy was Sz. So we had was IH bar Sz, I should say. So when we take those the eigenvalue for S sub z, we get h bar over 2, and we end up with this uncertainty relationship for our spin 1/2 system, that the uncertainty in S sub x and S sub y multiplied together has to be greater than or equal to h bar over 2. And this all came from the general sort of principle that if we have two observables, the uncertainty in those two observables has to be greater than or equal to 1/2 essentially their commutator, the magnitude, the time average magnitude. So with momentum and position, the uncertainty relationship is the uncertainty in momentum and the uncertainty in position is going to be 1/2 their commutator, right? And we can figure out their commutator by essentially just going through it, right? The commutator of momentum and position operators, well, they have to act on something. So we put some general ket there, but it's essentially how px operating on that ket minus xp operating on that ket. And if they're compatible observables, the order, they commute. The order wouldn't matter because they would share eigenstates, and we would just get 0. You can know both of them precisely. However, these don't commute, and we can see what that commutator is by looking at the position space representations of those, right? So we know the momentum operator is negative I h bar, the derivative with respect to position, and the position operator is just x, that position. So if we operate those in that order on our wave function and then subtract them operating on the other order, we get this. We have to do the chain rule when we take this derivative here. So that actually becomes, the derivative of x with respect to x is just 1, so we get this term, and then we get I h bar x, the derivative of the wave function. And they're both minus, because this minus sign. On this side, we just get the derivative of the wave function times I h bar x. These two terms cancel, and we're left with this. The commutator ends up being equal to negative I h bar in this case. So if we take that, now that we figured out the commutator, and plug it back into our relationship for our uncertainty relation, we're just going to get, the magnitude of that I h bar, or what is our familiar from pop culture, previous courses, maybe you've heard of this, the Heisenberg uncertainty relation, where the uncertainty in momentum times the uncertainty in position is greater than or equal to h bar over 2. Again, if we think of the example we did with position space and momentum space wave functions, where we had the Gaussian example, we saw the same sort of thing. The real space wave function was this localized packet that had some uncertainty characterized by the Gaussian standard deviation of delta x, and in momentum we had a delta p, and there was this relationship where the larger the wave packet was, the narrower the momentum space wave function was, and vice versa. As one got thinner, the other got wider. And it turns out that these Gaussian wave functions are actually the minimum the minimum uncertainty wave functions for this relationship. So again, delta p, delta x equal to h bar over 2 is the smallest sort of combined uncertainty you can get. And that happens when we have Gaussian wave packets. If you recall even further, as we went along, in those Gaussian examples, we had the uncertainty in the momentum was equal to beta, and the uncertainty in x was h bar over 2 beta times this term here. The interesting thing with this is there's a time dependence here, right? So at t equals 0, our uncertainty in position is at a minimum, right? As time goes on, this real space or this position space wave function is going to start to broaden. That was one of the things we saw in the last video. And that means that the t equals 0 uncertainty for these position and momentum space uncertainties is our minimum uncertainty for a particle, and it's going to grow from there. And we see that if we, just plug in these uncertainties into our, multiply them together, we get this, and that's going to just grow. So the minimum uncertainty is going to be at t equals 0. And you can see this, right? You plug in t equals 0, this whole square root term goes to 1, and we have delta p delta x is equal to h bar over 2, the minimum value of our Heisenberg uncertainty relation. So that's sort of the gist of the Heisenberg uncertainty relationship. It stems from, we have this, that position and momentum are incompatible observables, but you can sort of wrap your head around this as sort of a property of waves too, right? If you have a well-defined wavelength, you have a worse defined sort of position of that wave, and we have momentum space and position space wave functions for these particles. Another thing that these are very useful for, or the Heisenberg uncertainty relationship for, is back of the envelope type calculations. You can get rough estimates of energies of certain systems using this, right? So we saw that the energy of a free particle was just the momentum eigenvalue squared divided by 2m. So if we imagine, say, a particle confined in a well of length L, we might be able to say, well, I know the uncertainty of that position is, well, it's in the middle of the well, L plus or minus L over 2 might be an estimate for your uncertainty in the position of that particle. So that means if I look at the Heisenberg uncertainty relationship, delta p delta x greater than or equal to h bar over 2, the minimum uncertainty in my momentum would be h bar over 2 delta x, or h bar over L, right? If I plug in that L over 2. So the minimum momentum I can have is h bar over L, right? That is how you can get sort of an estimate for that minimum momentum. Is just look at what momentum would give you the equivalence in the Heisenberg uncertainty. Once you have that, you can just use that minimum momentum and say, all right, the minimum energy I could have for that particle would be p squared over 2m. And if I plug in that h bar over L for my momentum, I get h bar squared over 2m L squared, right? So that's an estimate for the minimum possible energy of that of a particle in that well. Now we solved a particle in an infinite well of length L, and the exact solution we got for that ground state was h bar squared over 2ml squared times pi squared. So we got essentially the same thing to within this factor of pi squared, which isn't exactly insignificant, but we're getting, if you take it with a grain of salt, that this is just a rough sort of ballpark estimate for that the energy of that state, it's pretty good. We also got the correct dependence on size. We got that L squared dependence on size. So these can be kind of really useful. You can imagine having some particle confined in a weird potential. It might take you a lot of time to, say, numerically solve for an energy eigenstate or something like that. And you might not need all that accuracy in your estimate if you're just trying to see if things are feasible. You can use these sort of the Heisenberg uncertainty relations to sort of estimate a ballpark number for what those could be. Anyway, today's video is kind of short. Heisenberg uncertainty relationship, momentum and position are incompatible observables. Uh, if you have any questions, please reach out to me and I will see you in our synchronous sessions.